We've defined what it means to be a power series, and we've also looked at the idea that if I plug in different values for x, that can affect whether or not the power series converges. So the goal now is to try to look and determine the values of x for which a specific power series converges. One thing that we can start off with, if I focus on my generic power series with terms c sub k times x minus a to the k, where we let k range from 0 to infinity, if I were to write out the terms, I would get c sub 0 plus c1 times x minus a plus c2 times x minus a squared, and so on. And if I plug in specifically the center, x equals a, notice that all of the terms will vanish except that very first constant term, because you're multiplying by 0, and we'll end up with c sub 0. Remember that in the power series, we're assuming that our coefficients, c sub k, are some finite values. So seeing that this sum is finite, we get that this would converge. And this leads to a fact that we can use from here on out. Every power series automatically converges at its center. So the question we're now interested in is, where else does it converge if it does in fact converge anywhere other than the center? So we're going to start to define some terms now, both the radius and the interval of convergence that relate to a power series. For the radius of convergence, let's call it r, again of my power series with terms c sub k times x minus a to the k, it's going to satisfy one of three things. So at one extreme, the radius could be infinity if the power series converges for all possible values of x. At the other extreme, it could be 0 if the only place it converges is at the center, x equals a. And then more interestingly, the kind of in-between cases, is that if r is something between 0 and infinity, it represents the positive number such that the power series converges when the absolute value of x minus a is strictly less than r, and diverges when that absolute value is strictly greater than r. So to get a little bit of a visual here, with the term radius, typically we think of two-dimensional things, and think of, for instance, the radius of a circle. But what I want to consider here is that if I view a number line of x values, think of the center here. So this is my x values. Like I said, we know that every power series converges at a. And what I'd like to focus on just visually is maybe this third possibility. So at one extreme, the convergence is the whole line. That's when r is infinity. At the other, we said it's just at a. But if r is some finite positive number, then what we're saying here is if you consider the values of x that satisfy this inequality, that's really saying that x minus a is either strictly less than r or strictly greater than negative r. And if you want to make a statement then about x, that means that x would be greater than a minus r and less than a plus r. So I could find these values for x on my number line here. And the idea is that notice here that r is really quantifying how far I can move out from the center and still get convergence. So this is going to be measuring a distance. Notice then that r is always a positive number, or 0, I should say. And it's symmetric here, the way we apply r around the center a. And so that's a little bit of an idea for why this comes with the term radius. The other thing to consider here is that once I view this on my number line, what I start to envision is a potential interval of values at which my power series converges. And we're going to call that the interval of convergence. So again, the interval of convergence for a power series is simply the interval that contains all values of x for which the power series converges. If we consider the possibilities, again, at one extreme, if the radius is infinity, this implies that the interval is from minus infinity to infinity, the whole real line. At another extreme, if r, the radius, is 0, then the interval contains a single point, and so we can use these curly brackets to express that the only point in the interval is a. I'll point out that if it makes or feels more comfortable, you could likewise say the interval is x equals a. Just as up here, we could say that this is the interval. So there's just different ways of using that notation. And then finally, if r is some finite positive number, what makes this a little bit more complicated is that there are actually 4 possibilities. because I'll come back up to that third case. Notice that nothing was said about the possibility that this absolute value is equal to the radius, meaning that there's some ambiguity about what happens at these points. We call these the endpoints of the interval. Consequently, when we fall into this third situation, we can't simply jump from the radius to the interval. What we have to do, we call it checking endpoints. So we need to then potentially look at those two series, the ones we get when we plug in x equal to a minus r, and the one when we plug in x equals a plus r, and we need to individually decide if those converge. All of this, I hope, will make more sense once we have some examples, which I'll go through soon, to actually find the radius and the interval for different power series. One big thing that I do want to mention here, though, is this whole notion of the radius of convergence and then consequently the interval. So we've defined this here, but this definition doesn't really give insight into how one would find R. Again, that will be clearer when we see an example, but the way we do that is the ratio test. So we're going to see that the ratio test has a huge role in power series. And once we get to a point where we might have to check the endpoints of our interval of convergence, then we can't use the ratio test because those are going to be the points at which the ratio test involves a limit of 1 being inconclusive. So all of this will come out in another video when I'm going to go through some specific examples one by one where we really look at finding the radius and the interval for different power series.